The next type of polar graph that I want us to be familiar with is called a limacon. Limacon, the way that is pronounced. And there's two types. There's a limacon without an inner loop. Okay. And there's a limacon with an inner loop. And that won't make much sense until we see both types. Now, and I'm going to introduce those. But first we're going to talk about limacons without an inner loop. Okay, that's what we're going to talk about first. And so let me write down some examples, some equation examples, and we'll graph two or more of these. But one would be r is equal to 7 plus 5 times cosine of theta. Or it might read r is equal to 7 minus 5 times cosine of theta. Or it might be, we might have something like r is equal to 7 plus 5 times sine of theta. Or r is equal to 7 minus 5 times sine of theta. Now, in general, then, the general way this looks, let me write it out a little differently here. It's going to be one of these forms. R is equal to A, and either a plus or a minus, B times cosine theta, or the other possibility is that we can have a sine of theta. So it could be R is equal to A plus or minus B times a sine of theta. Now the significant thing here is the relationship between A and B. We notice in the case that we're talking about here, in each of these examples, A was 7 and B was 5. And that says it all. Now, a limacon without an inner loop, that's what we're talking about. The condition is that the A has to be bigger than the B. A has to be bigger than B. And what this is going to look similar, it's going to look kind of like a heart again, okay? It's going to look similar to the cardioid. It doesn't have an inner loop, and that doesn't mean anything to us right now. But the indentation, unlike a cardioid, is not pointed. It's more curved at the indentation. So I guess it looks more like maybe an apple, you know, on its side or upside down or right side up, whatever. Another important piece here, it looks somewhat like a heart, looks kind of like a heart, a bit, so it's similar to the cardioid, but it does not go through the origin, does not contain the pole, is actually what that is, isn't it? Contain the pole. Again, we'll look at some examples real soon here, but here's the way we can tell that. Now I want to compare, we'll compare here in just a moment, but let's look at r is equal to 7 plus 5 times cosine of theta. And here's the whole issue about this r value. Because the cosine of theta, no matter what theta is, the cosine of theta is going to be between -1 and +1. So if we multiply cosine of theta by 5, that is, we multiply all the way through by 5, then we have -5 is less than 5 times cosine of theta, which is less than or equal to 5 times 1, which is 5. Now if we add 7 all the way through, of course 7 plus -5 is just a 2, isn't it? So we get a 2 there. Less than or equal to 7 plus 5 times cosine of theta. Less than or equal to, and a 7 plus a 5 is a 12. And here's the significance. What we have right inside here is the value of r. So what this says is that r is always, in this example, between 2 and 12. Always between 2 and 12. Well, the only way we can contain the origin is if we have an r value of 0. That's the only way the origin can be contained. So this is never going to touch the origin. And that's a lot different. See, this is a limacon. Okay, that's a big deal. A limacon without an inner loop. Without inner loop. And it's this relationship that the a value is bigger than the b value. If the a value is bigger than the b value, see, the worst cosine or sine can be is a -1 or a +1. And so if the a is larger, so if this number in front is larger, we can't subtract enough away to get to 0 because we only have a 5 in that position. Okay, so we can't subtract enough away from 7 to get something that is 0 or even negative. Now, just as a short comparison, remember with a cardioid, it might look something like r is equal to 5 plus 5 times cosine theta. And in this case, because cosine of theta can be a -1, then we can actually get an r value of 5. In fact, if we went through the same argument that we just did over to the left, again, cosine of theta is always between -1 and +1. Multiply through by 5, you have this. Now add a 5 all the way through. Well, if you add 5 to -5, you get 0. Of course, 5 plus 5 times cosine of theta, less than or equal to 5 plus 5 is 10. And of course, in the middle is our r. And so in this case, 5 plus 5 cosine theta is r. So in this case, with a cardioid, because the a and b are the same, if you will, we didn't say a and b are the same, we just said a plus a, didn't we? But since the a and b are the same, we will have a situation where r can be 0. And that's when we have it at the pole. Okay. So that's the idea behind it. Let's take this very first one. R is equal to, the very first example at the top, r is equal to, and I guess that's what I looked at there, 7 plus 5 times cosine theta. Now, let's make some notes before we graph. Note, we have symmetry. Cosine theta is involved. We have symmetry. And that symmetry is x-axis symmetry, isn't it? Now we know it's really, we're supposed to say polar axis, but we're using the idea of x-axis. Okay, so we know that amount already. And we might as well think about plotting a few points, and we'll kind of get the idea of how this is developing. So let's plot, let's choose thetas. I'm going to choose normal thetas, thetas that we would normally use, like a theta of 0. Well, if theta is 0, cosine of 0 is 1, and so our r is 7 plus 5, or 12. Well, I guess what I'm going to do next is let me at least start an axis over here. Okay, so I'll start an axis. Just let me draw that right now. Okay, what I've drawn here, of course, I've drawn an xy coordinate system, but as we plot, we're thinking in polar coordinates. And so an angle, and by the way, the little marks I've made for the indication for this graph, each of those marks is 2 units. So here is 2, 4, 6, 8, 10, 12, and so on. Okay, an angle of theta is the angle where we have no rotation at all, so it's just along the x-axis or polar axis. And in this case, our r value is 12, so we measure 12 units. Well, first there's 2, 4, 6, 8, 10, 12. That puts us at this position right here. Okay, now I'm going to let theta be pi over 2. And of course, the cosine of pi over 2 is 0. And so r is 7 plus 5 times 0, or r is simply 7. Okay, r is 7. So the angle pi over 2 is the vertical angle. It's the positive y-axis, isn't it? Or that's the terminal side at least. And so we need to measure 7 units along there. Well, this first mark is 2, second is 4, 6, 8 is up here, so 7 would be right there. So we're moving counterclockwise as this is being drawn. Okay. Now let's choose theta to be pi. Well, when theta is pi, cosine of theta is -1. So we get r is 7 plus 5 times -1. And of course, that's a value of 2. Now, remember, here's where we would have normally gone to the origin, but we're not here. I say normally, if we were dealing with a cardioid, that's what would have happened. But in this case, remember, the angle pi is the negative x-axis. We're actually going to the left from the origin. And we go 2 units then to the left, and so that puts us at this position right there. Okay, this is where 12 is. Remember, we're measuring an r value, so instead of putting a -2 on the x-axis like I normally would, that's 2 units for r. And of course, this was at 7. Okay. Now, if we choose theta to be 3 pi over 2, well, once again, the cosine would be 0 there, so we would get an r value of just 7. So here's 1, there's 2, 4, 6, 8 again. Remember, 3 pi over 2 is the is a vertical angle going down. As we rotate all the way down to the negative y-axis, and we're measuring down, 7 would put us at this position. So that's a value of 7 for r. Now that's not a whole lot of information for us, and so I'm going to add in a couple of extra points, and I'll fill that in and come right back to you. Well, I was calculating these extra points, and I see that I made a mistake here. Remember a moment ago when I marked off 2 comma pi for our point, the pi being going to the left, and 2, well, remember each of those hash marks was 2 units. And so I actually went 4 units instead of 2. The 2 would have been right there. So this is that point that I accidentally put in there incorrectly. What I did was look at an angle of pi over 4, of course, which is the angle that I have here on the right side, the dashed line, and I calculated approximately r being 10.5, and I put that point on here. I measured off approximately 10.5. And then I looked at the angle 3 pi over 4, which is the dashed line to the left there, and when I did that, I calculated my r to be approximately 3.5, and this point there is approximately 3.5. So what happens, and I'm doing this freehand, so please forgive me, it won't be perfect. We're going to move from this point, and we're coming up here, okay? And then we're going to come and hit this point, okay? And then we come and hit this point, whoops, I'm not doing a very good job there. And what happens is it dips in just a little bit, you know, and we'll see how much it dips in a little more later on, but dips in just a little bit right there, okay? Now we're going to have the same thing happen below. So we'll have this matching point. Remember, it's symmetric about the x-axis, isn't it? So what we're going to see below is it looks something, and that was kind of flat, but it looks something like this. Okay, and I'm sorry that that's not too pretty, but that's what I meant right here, is it is a little indent. It's not really pointed there. It is not pointed there. So it looks kind of like a cardioid laying on its side, but it's not pointed and it doesn't touch the origin. That's what that one will look like. I think what I will do next here is I will pause and get set up to show you some examples, some other examples, but we can kind of predict where these pieces are going to happen. I mean, notice that this point right here, for instance, that point right there, well, that was actually the when cosine of theta was 0, we got that 7 value, didn't we? See, and we got that 7 value. So that B kind of that A kind of showed up on the graph itself, didn't it? And this point right here is when we had cosine of theta being a positive 1. And so that was the 7 plus the 5 that we got right there, or the 12. So we can kind of predict those values. We're usually going to see the sum as the 7 plus 5 is going to be on the long side, if you will. and along the symmetry, the axis of symmetry, and the 7 alone, or the A alone, is going to be on the axis that we're not symmetric to. And we can always predict that, and we'll see some examples, like I said, as I set those up. Well, I'd like to look at some more examples of a limacon without an inner loop. And again, the without or with is not something that's clear yet, but we will see that in a moment. You can see the one that we just looked at, r is equal to 7 plus 5 times cosine theta, is drawn. And in this example, as you recall too, if theta is 0, that is when cosine of theta is 1, we get our biggest value of r, which was 7 plus 5, or 12. This is a position of 12. When theta is 0, when cosine of theta is 0, then our r value is 7. And that happens when theta is at pi over 2 and when theta is at 3 pi over 2. So this is that position value of 7 for r, and likewise here is a value of 7 for r. And the smallest r will be is when we create a 7 subtract 5. That's the smallest r could be. And that happens when cosine of theta is -1. And that will happen when theta is pi. So this position right here is the 7 minus 5, or 2, for an r value. Now, let me remind you again, as you see up here above, that the limacon without an inner loop is going to be a plus or minus, r is equal to a plus or minus 5 cosine theta, or r is equal to a either a plus or a minus sine of theta. And the indicator, the big issue here that makes this first, it's not a cardioid because the a and b are different values. That's the first thing. And it's a limacon without an inner loop because the a part is bigger than the b part. And what that means is the r value can never be 0 or it can never be negative, because we have, for instance, as the one we saw, 7 as being bigger than 5, and the worst we can do is subtract 5 from that 7. So we'll always have an r value that is positive. And the next one, it's very similar. I just want to make some points here as we're thinking of sketching these graphs. We'll say r is equal to 7 minus 5 times cosine of theta. Well, there's obviously a bit of difference here because of the subtraction sign. But the idea, once again, is we already know this is going to be symmetric about the polar axis or the x-axis because we're dealing only with cosine of theta. So we know that much already. Let me set this up so that we can sketch it. So there's the x-axis, if you will. Excuse me, the y-axis, pardon me. And now we get in here this x-axis. Okay. Now we know we're symmetric about the x-axis because of the cosine of theta. Here we are again. One of the things that we could think about is that we could kind of say, oh, well, where are we? What is r when theta is 0? What is r when theta is pi over 2? What is r when theta is pi? What is r? And so on. I'd like to think just a little differently now, kind of like we did just on the previous example. The biggest r can be is when we have a 7 plus a 5. Because after all, cosine of theta is always going to be between -1 and +1. So the biggest r can be is when we have a 7 plus a 5. The only way we're going to have a 7 plus a 5 is if cosine of theta is -1. And the only way cosine of theta is going to be -1 is if theta is actually pi. So the largest r value, that is most of this graph, is going to be when theta is pi, and then r will be 7 plus 5, 12. And so that's going to happen out here. Instead of on the right side of the x-axis, we're on the negative side, or the left side. Okay. Now the smallest theta will be on the other, excuse me, the smallest r will be on the other hand is when we actually have 7 minus 5. And we'll have that if the cosine of theta is 1, and that happens when theta is 0, the angle theta is 0. And so that's going to be right here. We will have a value of 2 for r, so that distance is 2. Okay, we'll kind of fill in the idea here in a moment, I hope. And, you know, if we don't have the minus or plus 5, that is, if we have r equals 7, that is, if theta is pi over 2, then cosine is 0, so r is just positive 7. That would be up here. And if cosine can also be 0 if theta is 3 pi over 2, so that's the downward angle. In that case, r would be 7 minus 0 again, and so that would be these positions. So here we're at a 7, and here it is 7. And we kind of have sketched out then what we're going to have. Now, the way this is going to start is we draw this. Remember, it's a limacon, and so it's got a dimple on this short side. That's what right over here. So that we're going to have a little dimple here. So that's what we're going to have. Let's go ahead and draw around. And remember, it's going to go through this point. And it's very circular-like, so it's going to come all around like this, and we're going to hit this point, okay? And then we'll continue around, and we'll hit this point, and then we'll continue around back to where we were. I'm not a perfect drawer, but there we go. So that's what it looks like if we have cosine involved. And you can kind of get an idea then how you expect the graph to look with cosine and the important parts and where the biggest part of the graph or most of the graph is going to lie. Now let's change the idea to see what it would look like if we're using the sine function. So for instance, if we were graphing r is equal to, let's say, 7 plus 5 sine of theta. Now in this case, we know that we're symmetric about the y-axis because we have sine of theta involved. And so this is going to be more or less a vertical, if you will, rather than laying on the side like above. We'll have something that's more vertical. So we'll have a top or a bottom, more or less. Let's set up our graph paper, or our axes, so that we can sketch this. Y-axis. X-axis. A little lopsided. And again, we could go through mentally, you know, we could go through and think, well, let's calculate some points. See, we could say, we'll choose some thetas like 0 and pi over 2 and pi and 3 pi over 2 and back to 2 pi and see where we are. And that's certainly acceptable. But what I want us to stop and think here, kind of like we did above, is where will r be the largest? Where are we going to be the furthest away from the pole? And that's when we have 7 plus 5. And the way we'll have a 7 plus 5 is if the sine of theta is actually 1. And the sine of theta is 1 when theta is pi over 2. So for this point, when theta is pi over 2, we'll actually have an r value of 7 plus 5, or 12. And so that means right here is going to be where 12 is. That means that's going to be the furthest position from the pole. Now, the closest position to the pole should be opposite of that. Let's just stop and think. Since we know it's a limacon, when we'll be closest to the pole is when r is the smallest it can be, and r will be the smallest when we actually have a 7 subtract 5. Well, of course, being a 2, and when would that happen? Well, that would happen when sine of theta is actually a negative 1. And the sine of theta is negative 1 when theta is 3 pi over 2. So when we're looking at the angle 3 pi over 2, of course that's down here, we know we have an r value of 7 minus 5, or 2. So that position is the 2 position. Of course, the r value is 2 there. So now we have the orientation thinking already that this is where that little dimple is, right there, is where the dimple is. This is the furthest away. Well, where is it going to cross the x-axis? Well, it's going to cross the x-axis in this case or the polar axis, when theta is 0. And of course, when theta is 0, sine of 0 is 0, so r is just the 7 value alone. Okay, so that tells us that this is the 7 position. And likewise, when theta is pi, sine of pi will be 0, so r is just 7 once again. And so that means right here is the 7th, well, there would be the 7th position, if we're thinking of that at the polar axis. As the x-axis, of course, that would be -7. So maybe we have an image of what this is going to look like. The graph would really start right in this position, because that's when theta would be 0. And then we're going to draw around. This is going to be the top of, if you will, or maybe the bottom if it's upside down, Limacon, and we move along here back to the 7 on this side, and then we come down here, whoops, here's a little dimple, okay, and then we continue and we finish the graph. One more while we're here, and let's suppose, just so that we kind of can see the cluster of these, what if we had r is equal to 7 minus 5 sine of theta? Well, what that's going to do, of course, is turn this graph upside down. Because here, the idea, let me get my graph papers ready. Okay, so here's the y-axis. Let's say along here is the x-axis. I'm kind of planning ahead because I'm expecting most of the graph to be below the x-axis. See, here's the issue this time. The biggest r value is going to be when we have a 7 minus 5, a 7 plus 5. So we've got to change that minus into a plus by having a sine value that is -1. And a sine value that's -1 happens when theta is 3 pi over 2. And of course, that's this downward, there's a downward vertical angle. So this is where we're going to be the furthest away from the pole when r is 7 plus 5. Now, we're going to be closest to the pole when r is 7 minus 5. And the only way we'll have a -5 is if the sine of theta is 1. And that will happen when theta is pi over 2. So right here is where we're going to be the closest to the pole. And that's where our little dimple is going to be again. That's where the dimple is going to be. And once again, when theta is 0, we'll have sine is 0 then. So we'll have r is 7 minus 0. And so along here is where our 7 is going to be. And likewise for pi, we'll have r is 7 also. Okay? So now we can draw this graph rather rapidly, because we have an idea of the shape already. Here's our dimple. Okay, come along. Change my hand position. I don't have a swivel hand. We move through here and back around to the beginning as we get to a theta value of 2 pi. So please take a look at these and understand, if you analyze it in the way we have been, you can make these sketches pretty quickly, and we don't have a lot to worry about when we go to make a sketch. Now, one thing I want to do next, before we leave these limacons without an inner loop, is I want to look at the relationship between A and B. Now, without an inner loop means A is bigger than B, but we could have an A of 7 and a B of 5 like we have here, but we could also have an A of 7 and a B of 6, or an A of 7 and a B of 3. I mean, we could have these A's and B's closer together is the issue that I'm trying to make, the point I'm trying to make. And so I'm going to prepare the next page with a few more examples, just so you can see what happens when we change the relationship between A and B. Yes, just what happens when A and B get closer together or further apart in their value. Remember, A is bigger than B, but what happens as those change? So I'd like to look at 3 different examples. 1 is equal to r is equal to 7 plus 6 times cosine of theta. Now, one that we've already looked at is r is equal to, 7 plus, I'm sorry for that goof up here, cosine of theta. That's one we've already looked at, and I'll write it down again as a comparison. And thirdly, let's look at r is equal to 7 plus 3 times cosine of theta. So you can see in the first case, 7 and 6 are just 1 unit apart, and the second 7 and 5 are 2 units apart, and the third 7 and 3 are 4 units apart. And it's going to make a difference on how what this limacon looks like. So let me draw the first one. You can see the first one is drawn, and it may not look too much different, but of course the largest r can be is 13 this time, 7 plus 6, and you see that out on the right. And the smallest r can be is 7 minus 6, which is 1, and you see that out on the left. In fact, if you compare this to what we just did, our little dimple here is a little more pronounced, isn't it? It's a little deeper of a dimple. It is not pointed at that dimple, but it's certainly a little deeper. And of course, the intermediate value, 7 and 7, we see on the y-axis. Now, on the other hand, when we graph 7 plus 5 cosine theta, which we've already done, we've had that in the past. Let me get our graph paper up here. In this case, the largest r value is going to be 7 plus 5, or 12. So out here is our 12. And the difference between 7 and 5, 7 minus 5 is 2. So over here is 2. And of course, down here is going to be our 7, and up here is going to be our 7 also. Now, when we draw this, what's going to happen, it's going to look very similar for a long time. Okay, it's going to look very similar, of course, a little different values. And what's going to happen here is we do have a dimple, but it's not nearly as pronounced. There's our dimple. Okay, it's not nearly as pronounced. And we move along, get back to here. Okay. Now, so it appears, of course, right now, that as the difference between the A and B becomes greater, then maybe our dimple is a little less pronounced. And let's see that that, in fact, is true also with the next example. R is equal to 7 plus 3 cosine theta. So as we get our graph paper started, now, it takes a little more than what we're doing here. I kind of have an idea already of what these look like, but part of it we can certainly tell. And in this case, the largest r value is going to be a 7 plus 3. So this is going to be a 10 out here this time. And the smallest r value is going to be a 7 minus 3, which is a 4. So we're going to be out to a 4 here instead of the 2 and the 1 we had before. So the further they are apart, then it's kind of like we're pushing that dimple further out. That's what was going on. If we push that dimple further out, we're getting closer and closer to something that looks kind of like a circle. Okay, and of course, when theta is pi over 2, we have an r value of 7 plus 3 times 0, or 7. So we've got the 7 there, and we've got the 7 here. I guess I should have put that outside. Okay, so they're kind of my landmarks. Now I'm going to start drawing the graph, and as I draw this graph, everything looks like it's going like normal, except since we're not going in so much for our dimple, we can we just barely tell that we have a dimple. It's almost just looks like it's flat on that side. There is a tiny, tiny dimple, just harder for us to see. So we get some idea of what happens the further apart our A and B get, the less and less dimple we have, because that smallest r value is actually greater and greater. That's what happened, is the smallest r value got bigger and bigger, and it pushed that dimple out. Okay. Well, what I wanted to do on the next page is look at what a limacon with an inner loop looks like. We'll consider limacons with an inner loop and give you some description of why it looks that way. and then we'll be finished with the limacons. So let me pause to get the next page set up. Well, limacons with inner loops, the equations as I write this down in generality look very similar to what we just had, but here's the difference. In this case, we're dealing with the fact that A has to be smaller than B rather than greater than B that we had earlier. And that makes a lot of difference because, so for example, R is equal to 3 plus 7 times the sine of theta, we'll say. Now, here's the significance. When this happens, we can actually get an R value that's negative. And we can also get an R value that's 0. And we might not know what value of theta that it's going to be 0 so easily, but we could. Because we could certainly take 3 and subtract some value, 7 times some value, which would be giving us a negative 3, 3 subtract 3, which could give us an R value of 0. So kind of like we did before, let me just point out, since the sine of theta is always going to be between positive 1 and negative 1. It's always between positive 1 and negative 1. Well, if I were to multiply through here by a 7, then I would have negative 7 is less than or equal to 7 times sine of theta is less than or equal to 7 times 1, or 7. And then if I were to add a 3 all the way through this, so a 3 plus a negative 7, less than or equal to 3 plus 7 times sine of theta is less than or equal to 3 plus a 7. And of course, in simplified form, that's a negative 4 is less than or equal to 3 plus 7 sine of theta, less than or equal to 10. And of course, 3 plus sine of theta is nothing more than our R value. So this is telling us that we're going to have R values anywhere from negative 4 to positive 10. Anywhere from negative 4 to positive 10. So what's going to happen to us, let me set up a coordinate system, some graphing paper for us, so that we'll be able to deal with this. And let me pause to get that drawn. Okay, here's my coordinate system. And as I start thinking about this, okay, and that's kind of again the idea, but I don't want to belabor with just a bunch of points. But suppose, I look at this equation and I say, okay, well, the biggest R can be is 10, 3 plus 7. Because the biggest sine of theta can be is a 1. And we already decided that over here, that the biggest R could be is a 10, didn't we? Well, when's that going to happen? That's going to happen when sine of theta is 1. And sine of theta is 1, I'm kind of in the middle of this, when theta is actually pi over 2. So that's when we're going to have an R value of 10, isn't it? And that's going to be right up here. So that's the 10 position. Okay? I guess maybe I should have started and said, okay, well now, if theta is 0, then what we're going to have is sine of 0, which is 0, so we're going to have an R value of 3. And this is where 3 would be, okay, right there. So that's kind of our starting point. So we're going to end up drawing here kind of a, oh, and by the way, this is symmetric to the y-axis, isn't it? Okay, so we're going to have something that looks kind of like this, and we know that we're going to have something matching on the other side, but we're far from finished. It was circular in nature, okay? And then, of course, the next time sine of theta is going to be 0 is when theta is equal to pi. And when theta is pi, then we have R is equal to 3 plus sine times 0. I mean, sine of 0. 3 times 0. Say it again. R is equal to 3 plus 7 times 0. That's when theta is pi. So R would be 3 again. And when we're talking about the angle pi, we're over here, aren't we? Okay? So that's at 3 again, the value 3R. We're 3 units from the pole. So we're moving along, and we continue down along this shape. We might need some more angles to really understand that it looks like that so far. But here before long, things are going to start falling apart, I think. Let's suppose theta is, let me say this, let me suppose theta is, the next thing would be 3 pi over 2. The problem with 3 pi over 2 is the sine of theta would actually be -1, wouldn't it? See, we would have r is 3 plus 7 times the sine of 3 pi over 2. Okay? And the sine of 3 pi over 2 is actually -1. So we have 3 plus 7 times -1, or 3 minus 7, or a -4. A -4. I didn't get that in there. So it's at 3 pi over 2, we have our smallest r value. Well, 3 pi over 2 is the angle is going downward here, isn't it? And if our r value is -4, we go in the opposite direction. So we go 4 units in the opposite direction. So we've gone that 4 units. So all of a sudden we're inside. Now remember, we were here. See, we were right here, and we were doing a circular motion. What's actually going to happen is it's going to continue down, in this case, just a little bit, and then it's going to go through the origin. That's not clear for us now, but I'm telling you that it will. And then it's going to continue in the circular motion, and it's going to hit this point. Now, because of the symmetry about the y-axis, then we kind of can see what else is going to happen. It's going to turn around now, and it's going to come back down and go back through the origin, and it's just going to go a little bit below this axis to have a circular shape, and we're going to have something that looks like that. And that's why it's called with an inner loop. And that inner loop happened because we had a negative r value. That's why that happened. Well, the size of that inner loop depends on how much difference there is between A and B. Obviously, if we have the difference between A and B here was 4, so we ended up with a 3 minus 7, which gave us a -4. So that inner loop was quite a ways inside. On our next example, in fact, I'll draw a couple more examples here just to get us used to this, but and I'll do that on the next page. But the difference between the A and B will tell us how deep that inner loop is into the limacon. Okay, this time, as opposed to r equal 3 plus 7 sine of theta, let's graph r is equal to 5 plus sine of, let's say, cosine of theta. And over here, let's graph r is equal to 5 minus sine of cosine of theta. Just obviously the difference between the A and the B are still the same. A is 5 and B is 7. Now, in both of these, and let's look at the one on the left, r is equal to 5 plus 7 cosine theta. This is going to be symmetric about the x-axis, isn't it? So it's going to lie on its side as opposed to what we just saw. Now, the numbers 5 and 7, sometimes I'm going to have a 5 plus a 7. Sometimes I'm going to have a 5 minus a 7. Sometimes I'm going to have a 5 plus a 0. So 5 plus 7, 5 minus 7, 5 plus 0, those are going to all be important things. Now, when am I going to have 5 plus a 7? I'm going to have that when cosine is 1, and that's going to happen when theta is 0. So 5 plus 7 will be our biggest value of r, furthest we are from the pole, 5 plus 7 being 12, and that's along the x-axis when theta is equal to 0. Okay? So that number shows up. Now the smallest the smallest r will be is when we have a 5 minus a 7. And we're going to get a minus 7 if cosine of theta is -1. And that's going to happen when theta is pi. And of course, theta being pi is out here. And so our R value is 5 minus 7, or negative 2. So it makes us go into or inside the loop. So we're going 2 units to the right instead of along the angle pi. And so there's 2, that because we actually have a negative 2r. We're going back into the loop. Now when cosine of theta is 0, r is just 5, and cosine of theta is 0 when theta is either pi over 2, so we'll be at 5 position there, or if it's at 3 pi over 2, so we'll be at a 5 position there. Now as we draw this graph, this is what it's going to look like. Okay, so we start out here, come along in a circular motion. Whoops. We'll go through this point. Comes around, it goes through the origin, but because of that negative r, it's got to reach back inside here like this. Okay? And then we continue until we get back to where we started. Okay, so here the 5 and the 7 were closer together than the 3 and the 7. So our loop is smaller. Our loop is 2 units into, if you will, the limacon, as opposed to before it was 4 units into, and so the loop ended up looking bigger. Now on the other hand, this the graph over here on the right, r is equal to 5 minus 7 cosine theta, we're still going to have all the same numbers, except things are going to be reversed along the x-axis. Simply meaning this, we still are going to be symmetric about the x-axis. But this time our r is biggest when we have, well, 5 plus 7, which means we have to have a negative 1, we're multiplying with that 7. So when cosine of theta is negative 1 is when we have an angle of pi. So it's in this direction that we'll have an r value of 12. Now on the other hand, you know, the smallest r will be is when we have a 5 minus 7, and that will happen when cosine is 1. And cosine will be 1 when theta is 0. So when we're looking at this angle, theta 0, we actually get an r of 5 minus 7, which means we go in the opposite direction 2 units. So we'll go inside 2 units. We're going to the left now, 2 units. And of course, when theta is pi over 2 is when we'd have r is equal to 5 minus 7 times 0. That's where the 5 is. This is where the 5 is for 3 pi over 2. We could still have 5 minus 7 times 0. So now as we draw this, where we would actually start here would be on the inside. See, if theta is 0, then r is 5 minus 7, negative 2. And so we're actually starting at this position, which is inside. And what would happen is we would move along the curve, go through the origin, hit the point up here, come across, come down, hit our furthest unit away from the pole, furthest distance away from the pole, continue our motion, hit the 5 here, finally get back to the origin, and complete our inside loop. And that's the way we would complete that inside loop. So I hope this gives you some idea about these limacons, and now you see why without an inner loop and within an inner loop. Remember, without is because the A was bigger than B, we never got a negative R value or even a 0 R value. But when A is smaller than B, we get a negative R value, and that's what causes it to go inside and make that loop. Well, the next type of curve I want you to be familiar with is called a set of rose curves. And so I'm going to get us set up on the next page for dealing with rose curves.